Hello dear friends, welcome to this video. In this video, as I said, we'll be discussing about the proof of the converse of the theorem. We have already proved the one part of the theorem. This is the second part. If you haven't watched the first part, please go through the videos and check the first part. In this video, we'll be proving that if a function preserves in a product, then it is going to be an isometry preserving origin. In the last video, we had proved that if it is an isometry preserving origin, that function will be preserving in a product. So let's just start the proof of this without wasting much of the time. So I start my proof like this. Let my f be a function from Rn to Rn such that f preserves in a product. So if I say my f preserves in a product, that means what? That means my inner product of xy would be same as inner product of f of x with f of y. Based on this property, I need to prove that it is an isometry. That means it preserves the distance, and with that it should preserve the origin as well. Let's just do this in part by part. My first claim is to prove that it preserves the distance. That means my norm of x minus y must be same as norm of f of x minus f of y. I need to prove this to prove it is an isometry, and this is for any x and y. So what we do is we start with a norm of f of x minus f of y the square. Since we know the property of the inner product is if I have norm of x, inner product of x with x, that is same as norm x square. So based on this, I can write this norm square is same as inner product of f of x minus f of y with itself. So it is going to be f of x minus f of y. What we do next is nothing but we just distribute this inner product. We are using the property of inner product being linear. So now what I do is I can write the first term over here with the first over here. So it becomes inner product of f of x with f of x. Then what we can write is we can write this is same as this x will go with this last term, so it becomes inner product of f of x, f of y. Similarly, this will go with this, so it is minus inner product of f of y with f of x, and at the end this f of y will go with this f of y, but both are minus, so it becomes positive f of y with f of y. Now, based on this assumption, what we know, whenever you have an inner product in terms of f of x, whenever you have an inner product in terms of this f of x, you can write on it place this only. So what I can see this is same as inner product of x with x. I can see this is nothing but inner product of x with y. I can see this is nothing but inner product of y with x, and I also can see the last one is nothing but inner product of y with y. By this one we can do this by our assumption, right? So this is same as what? Can I see this is basically equal to inner product of x minus y with x minus y. If you will open this inner product again, you get the same thing. So that is same as what? Inner product of something with itself is equal to the norm of it the whole square, right? Norm of its square. You started with this norm square and you found it is same as this. So therefore, by taking square root, or I will say positive square root on both the side, as we know the norms are always positive or equal to 0, we can say that this norm of f of x minus f of y would be equal to norm of x minus y only by just taking square root. Right? Is it fine? True? Okay. So this is the thing, but proving that if it is preserving inner product, then it is going to be isometric. Therefore, my f is an isometry. But we just don't want it to be isometry. We want it to be isometry preserving origin. So now my claim is I want to prove that my second claim is nothing but to prove that it is preserving origin. What does it mean? It means f of 0 must be 0. I want to prove my f of 0 is equal to 0. How I can think about this? What I can do is, again I will use 1. In 1, this assumption I will put x and y both equal to 0. What will happen? It will become inner product of 0 with 0 is same as inner product of f of 0 with f of 0. So inner product of 0 with itself is 0, right? Inner product of any number with 0 is 0. So with 0, 0 will give you 0 only, right? Okay. Now, what is the other part? What is the right hand side? That is nothing but norm of f of 0 the whole square. But if I take square root on both the sides, I'll get f of 0. The norm of f of 0 is 0. Can you tell me which is that vector having the norm value 0? What is a possibility for it? Over here I am telling you my f of 0 is such a vector which has a norm equal to 0. This implies me that vector f of 0 must be 0. Because the norm can be 0 only if that vector is 0, otherwise it is not possible. Right? So here we have proved both the things, that if a function preserves inner product, it is going to be isometry. That means it will preserve distance as well as it is going to preserve origin. Okay. So this is about this. But at the end of the video, I like to give you a small exercise that prove that the only isometry in Rn which fix origin and standard basis is going to be only identity. A very good exercise for the students. Please try to do it. If you are unable to do it, let me know in the comment section. We'll discuss it in the future videos. And at the end, thank you so much for watching this video till the end. I hope you like it. Please like, share and subscribe to the channel. Okay ji, bye bye.